In this lesson, I will provide an overview to remote sensing. Remote sensing in its broadest definition refers to collecting information about an object without being in direct physical contact with it. In other words, learning without touching. The remote sensing process, which can be described in greater detail on the next slide, involves acquiring, processing, and analyzing data about a target. In the remote sensing process, data is collected using either a ground, air, or a spaceborne instrument. The data is then converted from analog to a digital representation, and in order to gain knowledge from the target, information is extracted for analysis. For our application, we use radar systems to obtain bedrock, surface, and internal layer imagery from Greenland and Antarctica, and we are interested in identifying layers since these image features determine the ice thickness and accumulation as it relates to global climate change. To give a historical perspective on the use of remote sensing, the first photos from a plane were taken in 1908 and used during World War I for enemy surveys. The war improved the camera quality and photos were taken at 15,000 feet. Other historical examples of remote sensing include the 1903 Bavarian Pigeon Corps, where carrier pigeons with light camera. Other historical examples of remote sensing include the 1903 Bavarian Pigeon Corps, where carrier pigeons with light cameras were used to take pictures every 30 seconds of an observation. The pigeon photography were displayed in 1909 in Dresden International Photographic Exhibition. The first requirement for remote sensing is to have an energy source, which provides electromagnetic energy to the target of interest. As energy travels from its source to the target, it interacts with the atmosphere. Once energy passes through the atmosphere, it interacts with the target depending on the properties of both the target and the radiation. After the energy has been scattered by or emitted from the target, a sensor collects and records the electromagnetic radiation. The energy recorded by the sensor is transmitted to a receiving and processing station where the data are processed into an image. The processed image is interpreted in order to better understand it and reveal new information for solving a particular problem. The processed image is interpreted in order to better understand it and reveal new information for solving a particular problem. There are two types of sensors in remote sensing, passive and active. Passive sensors can be used to detect energy when the naturally occurring energy is available. For all reflected energy, this can only take place during the time when the sun is illuminating the earth. Energy which is naturally emitted can be detected day or night as long as the amount of energy is large enough to be recorded. Active sensors, however, include the ability to obtain measurements anytime, regardless of the time of day or season. Active sensors can be used for examining wavelengths which are not sufficiently provided by the sun, such as microwaves, or to better control the way a target is illuminated. Active sensors, on the other hand, require large amounts of energy to adequately illuminate targets. Remember, remote sensing requires a source to illuminate a target. This form of energy is electromagnetic radiation, and it consists of an electrical field which varies in magnitude in a direction perpendicular to the direction in which the radiation is traveling. The magnetic field is oriented at right angles to the electrical field. Both these fields travel at the speed of light. The electromagnetic spectrum ranges from the shorter wavelengths, including gamma and X-rays, to the longer wavelengths, including microwaves and broadcast radio waves. The next few slides will highlight the regions of the electromagnetic spectrum which are most useful for remote sensing of the Earth. For most purposes, the ultraviolet or UV portion of the spectrum has the shortest wavelengths, which are practical for remote sensing. This radiation is just beyond the violet portion of the visible wavelength, hence its name. Some Earth's surface materials, primarily rocks and minerals, emit visible light when illuminated by ultraviolet radiation. The light our eyes detect is part of the visual spectrum. Blue, green, and red are the primary colors or wavelengths of the visual spectrum. No single primary color can be created from the other two, but all other colors can be formed by combining the primary colors in various proportions. Although we perceive sunlight as a uniform color, it is actually composed of various wavelengths of radiation and primarily the ultraviolet, visible, and infrared portions of the spectrum. The visible portion of this radiation can be shown in its component colors when sunlight is passed through a prism, which bends light in differing amounts according to the wavelength. The visible portion of this radiation can be shown in its component colors when sunlight is passed through a prism which bends light in differing amounts according to the wavelength. Infrared images obtained by sensors in satellites and airplanes can yield important information on the health of crops and can help determine forest fires when they are masked by a curtain of smoke. Microwave wavelengths range from approximately 1 millimeter, which is the thickness of a pencil lead, to 30 centimeters.